Hello, hello. What is up, internet? I'm back with more Get into Mathematical Logic. So, last week we kind of went over the truth function aspect of this weird abstract language that we're studying that is expressed through big capital letters, which we have mentioned stand in for propositions. We've been exploring several methods to visualize this combinatory matrix. Basically, the fact that each different propositional letter can be assigned one of two values, either true or false, and must be assigned at least once. That creates in formal terms, we call it a combinatory space. But it's not very intuitive to call it a space just now for the beginners out there. When mathematicians and logicians use the word space or call something a space, we're not being literal. It's not physical space we're talking about. It's more of a lattice, like a structured pattern in which certain formulas can take place. And the fact that these formulas take place in this arrangement of possibility is what intuitively makes us call these mathematical structures a space. But if I have to be literal, what they are is a form of web or ring. Like the technical term is lattice. Let me try to visualize it. So yeah, if we have through two propositional letters and two possible values, so we have our classic P and Q. Now we have four possible states. The state in which both are true, the first is true and the other is false, false, true, and the state in which both are false. And this creates or we can visualize it as some sort of diamond pattern thing in which there is a top and a bottom. And the top is everything is true, and the bottom is everything is false. And the things in the middle are some of them being true and some of them being false. Now, when you only have two values or two propositional letters, it's a very simple structure. When you have three, the diamond multiplies into something more visually akin to a lattice. You have this diamond, and it kind of replicates. It would be PQR, PQ, PR, PQR, 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 QR, QR. Okay, I think this is kind of how it goes. So you have three letters. You have the case in which all of them are true. All of them are false. Two are true. One is true and two false. Okay, I definitely fucked up the visualization. Or did I? Oh yeah, no, I'm so yeah, this is when you only know the value of 2, so it's true and false, false and true, and then you have true, true, false, true, false, true, true, false, false. I'm gonna run out of space. Hey! Hello, Bones. How you doing? Sorry, but my chat overlay program disappeared from my computer. I have no idea how it happened. It may have something to do with the Arch Linux archive getting bapped. Oh, okay. Yeah, I know why I messed up. It's because you're supposed to draw it in 3 dimensions. It's not supposed to be flat. It is. It has like depth. Just like this, and then I'm gonna use grayish halftone. Well, let me just copy it over visually so I don't mess it up. Kind of like this. There we go. Again, this is not like any rigorous definition. This is just like a way of visualizing why mathematicians call it a space. Oh no, hangover. Well, try to rest up and drink as much water as you can. So this stop will be P, Q, R. This is P and Q. This is P and R. This is Q and R. And then the versions that are negated, it will be not P, or rather, yeah, false. So rigorously speaking, this will be, yeah, PQ and R being false or negated. This will be not Q, and this will be not P. Okay, yeah, it is making more sense now. And this will be where 2 are negated and 1 is true, and so on. You get the combination, and then you eventually end up with the bottom of not P, not Q, not R. And because of this visual, three-dimensional depiction of the combinatory possibilities of just 3 things that can go in 2 ways, which the more computer savvy among you might realize, oh, it's a bit. We're talking about computer bits. Yeah. So if we have 3 bits, we have 8 possible spaces, or locations, like, which are the vertices in this diagram. Yeah, because you can visualize it this way. That is why we call it a possibility space or a space of the sort, even if it's not like anything closely intuitively meaningful to an actual physical space. Anyways, so we so far have been studying the relationship between our formula, our propositional letters, and the possibility spaces we can build with this. And we've been going through 2 methods, truth tables and tree proofs. Truth tables are really useful for providing an initial intuitive explanation of what it means to have like an exhaustive list of combinations. But the problem is that they are very inefficient because they grow exponentially. And then we went over another method last week, which are trees, which allow us to study properties such as tautologies, contradiction, contingency, and even logical consequence through this understanding of formula as possibility spaces. In the tradition of classical logic, this way of seeing formal systems through assigning the meaning as a possibility space is called the semantic method. If people watching this have any training in linguistics or language or literature and so on, they may know that word, semantics, which is the study of the meaning of words. The kind of meaning we assign this formula has nothing to do with actual semantics. It's just a distinction that stuck because, as today we'll start seeing, there are other methods which are called purely syntactic, in which we do not question the meaning of anything that we do. We just follow a set of precise syntactic rules and we'll get a result. In such a way, the syntactic method is very computer-like. It is very mechanized. It doesn't deal with interpretations. And technically speaking, when we say that this squiggly letter we call a Q or a P or whatever can have 1 or 2 values, that is technically, in a very abstract kind of way, an interpretation. It's just not an interpretation in any rich, actual human way. It's a mathematical kind of interpretation. Anyways, we went over 3 proofs last week, and I did some tree proofs in a somewhat hasty but still rigorous way. And I took some time to do some of the quote unquote homework in a completely rigorous machine like manner. There are automated proof programs that can do this. I just couldn't find any one that looked good and ran well on my system. There used to be like automated proof project called COQ. They changed the name, thankfully. It's no longer called Coq. It's now called Rock. But I couldn't get it to run on my system, sorry. So I just had to do it by hand, well, do it on the computer in a very methodical manner. So this very methodical manner involves numbering every step I take and justifying each step with a rule. So this is just an address or a way to refer to which formula I am applying a rule from and to. And in this column, it's a sequence of rules that justify or direct me in knowing how to manipulate this sequence of symbols. This method, this completely mechanistic and well-defined recursive method, is quite literally computing. It is a computable method. I am behaving like a computer. In fact, one of the things I like to talk about when I mention the history of logic and computation is that the first computers were not machines at all. They were humans, mostly women. When mathematicians from the 19th century wanted to crunch like a big amount of complex arithmetic, they had computers. And in that context, that meant like a room, anywhere from 4 to 20 people, maybe more. 20 people sitting in a room with pencil and paper, trained in making long-form calculations very quickly. That is what a computer was. The mathematician, the leader, the nominally important person that tried to prove a theorem or make some calculations, gave every computer, human computer, a set of precise instructions. And they just followed the instructions to the letter and crunched the numbers and gave the result to the mathematician, who then proved an actually conceptually interesting theorem or whatever. The idea of just processing mathematical inputs without asking what they mean or wondering about the meaning of any of this is the core experience of computation. Manipulation of symbols without interpretation. What we now call computation is the fact that we, and by we I mean humanity, devised a method for making electromechanical processes do the computing for us. We arrange rocks in a very specific way to crunch out the computation for us. The trade-off is that if you want to make a problem computable, you have to define it in a very precise way, such that it can be done without requiring any interpretation. The way I did these problems from the homework is an example of one such way. I will just follow a set of instructions that involve me recursively analyzing every formula that appears using a very specific method we call an algorithm. My algorithm is as follows. Every formula must be analyzed. If I spot a formula and its negation in the same branch, I must automatically close that branch and move on. Every formula can be analyzed or broken down into constituent parts by a very specific rule. That rule is defined by its main logical connective and whether or not it is negated. These rules we saw last week. I'll just paste them in the document for a refresher. Oh no. Oh no, transparencies! Oh, wait, never mind. There we go. I wasn't pasting in the topmost layer. Yep. If I see a conjunction, I will do this. If I see a disjunction, I will do this. And so on and so on. And this covers all of the formula that can be we have defined so far in our system of propositional logic. The only thing is whether it appears, whether the connective appears, or whether it appears with a negation applied to it, and that's it. That's all there is. And the last rule is that if I have analyzed every possible formula in a branch and the branch remains open, then I have provided a counter model to the initial query and I stop. I once took a very brief Haskell course in which I programmed a functioning 3-proof automatic prover. It is something that can be done without defining the terms. Hello, Rupert. Nice boga emote. Without defining the meaning of the words stop in anything but a mechanistic way. And by adapting that behavior, I have created this this version of the 3 proofs. Now, I want to emphasize, the way we did it last week is perfectly fine. But that had like some human ingenuity going on. Some of the lines were a little bit lax. Not every step was recursively justified. It's good. It counts as a proof, but it did not count as a computational proof. This, however, does. So for example, let's prove that Q implies that P implies Q. I think we did it last week, just not as rigorously. So we start by negating the formula we want to find if there are any counter models of. Oh, hello Anarchotaco. Welcome in, first time chatter. So I was saying, yeah, we want to see if there's a counter model. We want to see if there's a way of making this formula false and be consistent. So we start by negating, and this is justified by a special rule that's called premise. The premise rule is weird because it just basically means manual input. Premises are not present in the pure logical first order or propositional logic system. Introducing a premise just means I will introduce an arbitrary formula into the system. It is pure input. It is user-guided input. As such, it's not really a justification. It's more like a declaration of, okay, this is just arbitrary information entering the system. It does not come from the system. It comes from outside the system. But after that premise, everything is just mechanistic. Okay, I only have one formula. It is an implication, but negated. So I check my rules. Oh no, I deleted the rules. Anyways, so it's here anyways. I use the negated conditional rule, and I get the first part and the negation of the second part. And it's justified by negated, conditional. In which formula? The formula at 1. And as soon as the number formula appears here, the formula is considered analyzed. I don't need to analyze the same formula again, not in this method. Okay, now I have 2 more formulas, 2 and 3. I cannot keep analyzing 2. 2 is already an atomic formula. It has no constituent parts. But 3 has constituent parts. It is also a negated conditional. And so I apply the same rule, but this time I apply it to the formula at 3. So now I have Q, P, and not Q. Oh, look. I go up the branch, the only branch I have, and then I see that I have Q and not Q. Then, by my contradiction rule, I can join the formulas 2 and 5 that tell me Q is true, Q is not true, at the same time, in the same way that in formal logic is impossible, and therefore I can close this branch through the contradiction rule. The contradiction rule is different because I am not analyzing anything. In fact, I am joining together, I am synthesizing the information of 2 formulas. The formula at 2 and the formula at 5, together they generate a contradiction. Something being true and not true at the same time in the same way, which in the mathematical abstract world of propositional logic cannot be the case. Okay, then we have a slightly more interesting example from the homework. We have the implication of P implies Q, and I'm using the ampersand for this because it's just easier to see and type. And the implication of Q implies R. Now, with a little know-how that we went over last week, I know that this is basically an argument in which this are the premises and this is the consequence or conclusion. So now I could just start with this formula and negate it and so on, but it's just extra steps. I will just put everything joined together by the conjunction as a separate premise, and everything after the implication as the conclusion. But basically, I'm just saying this is the same as a negated implication. Affirm the antecedents and negate the consequent. Sorry for the awful doodles. So that's why I just skipped right ahead. There is no universal truth is a universal truth. I mean, yeah, I guess there are more elegant ways to solve the tension. Some of them include saying the notion of a universal truth is a confused statement. That way you don't have to engage in the paradox. I mean, if you want to, you can engage in the paradox if you want to. But I will keep insisting throughout this course that when I speak of truth and falsehood and similar terms, I'm using them as toys. I'm inside the world of propositional logic, and there is not a lot of philosophical importance to the kind of truth we're talking about. I think I mentioned in the first stream of this series, which I will now post the playlist. That we can understand the values of propositional logic by calling them true or false, 1 or 0, on and off, and so on. The underlying structure of propositional logic can be used for electricity. It can be used for Minecraft redstone. So it's not like necessarily a big, meaningful metaphysical truth when we are using this this language. Anyways, so I just saved myself a step here. It's redundant and it drags along when you do it every time. So I'll just assign this as a premises. Also, putting them like this, it's a little more intuitive when we want to prove. I was a licensed electrician. I am great on Minecraft redstone. Yeah, you got it. Perfect. Then you'll find this stream a little redundant at times. Anyways, so we want to prove something called the transitive property. What this means is that in propositional logic, if the first element implies the second, and the second implies the third, then the first implies the third. You can chain implications, you can piggyback them. If A implies B and B implies C, then A implies C. And as we proved in the second stream, this is a general enough schema for our entire system. So in this case, P does not necessarily have to be P. We can take it as a metavariable. We can talk about alpha. And Q can be understood as beta. So it's for any formula whatsoever. Any formula, if the first implies the second and the second implies the third, then you can skip the middleman and say that the first implies the third. This allows, or this rather means that in propositional logic you can have chains, which are a certain type of structure. Anything in a straight line, or anything that can be ordered in a straight line, is a type of chain. But not all chains are just straight. For example, you can have circular chains. A implies B, B implies C, C implies D, and D implies A. That loops back. And then, well, A implies B implies C implies D implies A, means that you loop back. And so, you get a cycle. So, really, the fun part about this is just that it's a fun mathematical structure, the transitive property. And it's something that you will see a lot in mathematics. Calling something transitive means basically that they follow this structure. That you can go from the first to the second to the third, and therefore from the first to the third, and so on. Another way of visualizing or understanding the transitive property. Yeah, transitive is the other direction. Recursive is when you go from the end to the beginning. Transitive is it just moves along. So yeah, So I know this is valid. I know that the transitive property applies to the conditional. But let's see how we went through this. Okay, so the first three formula are justified by them being premises. Then I will analyze the formula at 3 because it is the only one that doesn't split off branches. So 3 is a implication negated, so negation of the implication at 3 gives me P and not R, the affirmation of the antecedent and the negation of the consequent. Okay, I have analyzed 3. I have to analyze 1 or 2. So here I split off a branch. And this is why it's a pain in the ass to make 3 proofs this rigorous on a computer, because I mean, at least on paper I can just do whatever I want, but here in a computer I have to make it sure it's all monospaced and has the same width and so on. So in 6, instead of just continuing with 1, 2, 3, 4, 5, 6, I make a split. I now have 6A and 6B. 6A is the first branch, 6B is the second branch. So 6A, I justify the split by implication of 1, and then I immediately close branch A in 7 by applying the contradiction rule for 4 and 6. 4 is P, 6, okay, here I missed, it should say 4 point A. Kind of looks like a 2. There, kind of looks like an A now. 4 and 6.A have a P and a not P. Therefore, that is a contradiction, and I close off this branch. So now I go to the other branch, 6.B. Okay, so far I have no contradiction, but I still have a formula to analyze, the implication at 2. I have to split up the branches again. Now I split the branch into 7.B and 7.C. And here I missed another. Here it should say 8.C. At 8.B I close the branch because 6.B and 7.B are Q and not Q, contradiction. Likewise in 8.C, 5, which is this one, and 7.C, which is this one, are R and not R, which is a contradiction, which means close, which means, of course, the transitive property is valid for the implication in propositional logic. Also, I hear my nieces. I think they are visiting me. I am so sorry if you hear children screaming. Okay, next one. This is the first direction of a logical property called De Morgan. Let me type it in chat. Named after a mathematician. Mathematician called Augustus De Morgan, who did a lot of work with Venn diagrams. Let me paste the diagrams here to show another connection between other branches of mathematics. So in Venn diagrams, the union of A and B is equivalent wait. the negation, the line on top means negation. So the negation of the union of A and B is equivalent, now we know what the symbol means, is equivalent to the intersection of not A and not B. So A is everything inside this circle, B is everything inside the circle, the intersection of A and B is this, and not A is everything outside A, not B is everything outside B. So for example, using the symbols that we now know, this space is not B, is A and not B, while this space is A, is B and not A, and this part in the middle is A and B. So not A, so the union of A and B is everything colored, and the negation of that is everything outside. So everything in blue is a negation of A union B. The negation of A is everything outside A, the negation of B is everything outside B, and the intersection of both is, again, everything blue. So De Morgan proved that these two statements, or these two spaces, are the same. And it goes the other way. The negation of the intersection of A and B is the same as the union of the negation of A with the negation of B. So everything in blue is equivalent. Now, wait, what's going on? There we go. So there is an equivalent to that in propositional logic. This is the negation of the union of A and B, in this we call them P and Q, means the intersection of the negation of not P and not Q. So we can prove that in with 3 proofs. Hold on. This should have this. I don't know where the lines went. So we start with the antecedent and the negation of the consequent, or the conclusion. So once again, I start by analyzing the formula that won't split up any branches, which is the negation of the disjunction at 1. So I get not P and not Q. And then I have the second branch, which is the negation of a conjunction, which gives me both parts negated in different branches. So now I split up my branch into 5 point A and 5 point B. 5 point A is not P. So because P was already negated, I have to add another negation. So instead of, if I add a negation to not P, I get not P. Likewise, if I have not Q and I add a negation, I get not Q. This is a contradiction. I have a formula and its negation. Not all contradictions need to be of the shape P and not P. I mean, technically this is P and not P, except that P in this case is not P. It's still a formula and its negation. That is what matters. So a formula and its negation in the same branch closes the branch, whether it's not P and P, or whether it is not Q and Q. This is, for human beings, it's a very inefficient way of doing things. What I wanted to do to showcase it like at least a bit to show what it's like to proceed under completely rigorous computational methods. Now, we have teased so far that the things we want to study. Let me switch from the homework to our workbook. That we are concerned with a particular mental process which we call inference. And inference, so far we have intuitively described it as extracting certain formula or certain content from an established set of premises. This is where we get into something that actually has actual philosophical weight. What does it mean to infer something from something else? What does it mean when someone says, "Oh yeah, well, it follows"? Or the negation, "It doesn't follow." Or when we say, "Well, not necessarily." I talked a bit about that comment of "not necessarily" last week. But now we face a particular problem. We want a mathematical model of inference. That is the whole thing, the whole reason why people started making these systems. That is the reason why Aristotle wrote a book about logic, to study the process of inference, the process of saying, hey, if this is true, then this other thing has to be true, based on this first thing. We all know the classic Aristotelic examples of every man is mortal, Socrates is a man, and the magic word, therefore Socrates is mortal. If the first two sentences are true, or we take them as valid, or we incorporate them as input into our system of thought, and we just know not what the word Socrates, mortal, or men mean, but what the words all and are mean, then we have to accept, we have to extract the content that if all men are mortal and Socrates is a man, then Socrates is mortal. Or, since we used Venn diagrams a little earlier, if I present to you two sets and I say that the first set is a subset, is the first set A, oops, can I make my yeah, okay. My first set A is a subset of a larger set B, and I say, well, the element X belongs to A, then if everything that belongs to A belongs to B, which is the definition of a subset, and X belongs to A, then X must also belong to B. In the case of the classic Aristotelian example, A is the set of men, human beings, and B is a set of mortals. Yeah, Rupert. The main goal in non-philosophical majors for propositional and first order logic is to get people into set theory. With set theory, you can do, I want to say, 99.99% of all mathematics humans have ever made. I mean, you can't. Doesn't mean you should, but you could. Yeah, in mathematics, first order logic is basically a propedeutic for set theory. Yeah, set theory is really powerful, and with first order logic alone and some extra symbols, you can express all mathematics done by most human beings. The remaining 5% is the mathematics done by absolute freaks. And I say that endearingly. Love my math major homies. But back to the example. This is just another way of expressing the relationship between concepts of all men are mortal, Socrates is a man, therefore Socrates is mortal. The first sentence is basically saying that the first set is a subset of the second one. Is our goat small enough to... Absolutely. Oh, absolutely. Like, have I posted a picture of the man? Can I paste it here? No, I can't. Oh, but I can do something better. Hold on. Professional streamer, everyone. There we go. That is Raymond Smullyan. In some late night TV show. I mean, much like Alan Moore, Raymond Smullyan was a magician. Like I'm not like fucking with y'all. The man was an actual magician. He did like magic tricks, illusionism. Like, okay, so Alan Moore is a magician in the sense that he practices ceremonial magic. Smullyan was a magician that did like party tricks and illusions and so on. But he was also a Taoist. He has a really cool book about Taoism, so that I also recommend. So yeah, the man was a total freak, and in the most positive of ways. Great guy, really great guy. And yeah, and like Alan Moore, he also looks like a stereotypical wizard. Hold on. I can do something even better. Hey. Anyways. I'm glad you purchased his book. Also purchase his book, What is the Name of This Book? And also purchase his book, Satan, Cantor, and the Infinite. Just banger names. Anyways, Venn diagrams. Thanks for the hydrate. Venn diagrams are a way of visualizing relationships between sets. Formal logic, propositional logic, is a way of expressing in a very abstract way a type of inference. Some philosophers see formal logic as a model of reasoning. As in, we have human reasoning, particularly deductive reasoning, and formal logic is a way of modeling that process. I personally disagree. The reason why I disagree are varied and plentiful. Many of them are in my thesis. And just for the sake of philosophical honesty, I like to make my stances clear. I don't think most human beings actually reason in the highly abstract mathematical way that formal logic wishes or claims to model. I think that instead of seeing formal logic as a model for how humans reason, I think we should see it as a guide, a guideline. It's not how we actually reason, it is a way we can learn how to reason under a very specific set of circumstances. Recently, and I have to vent, one of the people I even quoted him in my thesis and even talked to him in real life and thought that his work was pretty cool. I will not name him because of what follows. But I recently learned that this person, who I consider like an authority in a type of in an area of study near my field of study, let's leave it like that. I found out that this person is a hardcore Zionist, and much like other examples from the history of logic, starting with Cantor and Frege and Gödel and so on, I see again and again the selectiveness of human reasoning. How it's all bound up to ego and emotion and vibes, and thinking and reasoning in this highly abstract mathematical way requires a supreme effort. Exactly, anarcho-taco. Yes. So that is one of the reasons, and I can keep arguing with this because again, this is my thesis. I have written like literally hundreds of pages about this, so I can go on if necessary. But that's not what we're here for today. I just want to make clear that my position is that formal logic is not a model of human reasoning. We can see it as a guideline or as a specific case or a way we can learn to reason under very specific circumstances, but it is not a model in the sense that it recovers or rescues how humans intuitively reason. I don't believe that. Anyways. So that leaves us with a problem. What is an inference? What does it mean for something to follow? Philosophically, the question is vast and open. Personally, again, very importantly, personally, I believe that the best account for how logic treats the problem of inference is through information theory. Another reason why I speak of true and false, but in a very lowercase, relaxed, not committed kind of way. Because instead of talking about true and false in any meaningful manner of propositions being true or false, I like to think of them as information carriers. Yeah, again, philosophically apart from what we're studying today, I do not think human brains can be reduced to a computer, The reasons why are plentiful. An approach can be started with Hubert Dreyfus, what computers cannot do and what computers still cannot do. A warning: Dreyfus carries some water from Heidegger, and Heidegger is, I think, my least favorite philosopher ever made. 90% of the reason why I don't like Heidegger is because he was a Nazi, and I think that's a very good reason. Anyways, but regardless of that, Dreyfus does provide some valuable arguments or interesting arguments about how human brains and minds, which is another kind of worms, the brain and the mind, whether they are the same or not. I personally do not believe that the brain and the mind are the same thing, but I also do not believe that a mind is a metaphysical object. Yeah, it's a mess. Philosophy is all around us, and we're trying to do our best to not get lost in the sea of philosophy that is surrounding this enterprise. So I was saying that I found that the best account for how logic treats the problem or explains the problem of inference is through information theory. So instead of seeing P's and Q's as true or false or as propositions in a classical sense, I think of them as information carriers. And instead of true and false, in my mind, I just hear designated value and counter-designated value. Yeah, well, Anarcho-Deco, that is an excellent topic of conversation, but for another kind of stream. I have to stay focused because I want all of this to go to my YouTube, so I can have like a course. So I can only warn people about the philosophical implications, but I cannot cover them in this course. Just viewer be warned. There is metaphysics around if you're not careful. Or maybe you like metaphysics. I personally, not to. I personally try to subscribe to a immanentist understanding of things. But anyways. And part of that immanentist understanding of things involves treating logic as a type of information channel. So, how I personally found most clarifying and most easy to understand the role of logic when it comes to inference. Let me delete this wonderful Venn diagram. Is that formal deductive reasoning is not about finding new truths. It is about clarifying access to an already existing set of information. Let me explain. In our classical definition of, and by classical I mean propositional logic, classical definition of logical consequence, it has been so far that for every model that makes a set of premises, which we will call gamma. What's the symbol for? Let me copy paste the symbol for gamma. Yeah, uppercase gamma. Through all of those interpretations understood as truth functions must also make the conclusion, and the conclusion is usually alpha, true. There we go. That is our definition so far. And we have defined truth just as a truth function assignment, an arbitrary assignment that we map out through exhaustive mapping that we can visualize as truth tables, or that we can analyze with tree proofs. But ultimately, truth tables and tree proofs, those are methods. The underlying structure is abstract and not visible. It's just a relationship between functions and sets. Sets of what? Sets of propositional letters. The problem with this definition is that we don't have like a really meaningful or agreeable definition of what it means to be true. We have like a joke toy definition of truth, which is just I assign it this value. That's why under information theory, we don't care about calling it true, we just call it designated value. What makes something true? Oh, that I designated that value. So if it's just a purely arbitrary exercise in designation, why not call it something else? Yeah, why not call it something else? We can call it the poop value and the piece value. And we can say that for every model that makes premises poop, the interpretation must also be poop. Zizek will say reasoning is ideology, is spontaneous, and can be performed on your behalf by institutions. Oof. I will not call reasoning. I will call that association. The one virtue of formal logic is that it is the enemy of spontaneous thinking. It is rigorous, mechanistic, and done step by step. It has to be drawn out in grueling, precise fashion. And I am not saying that is the correct way to think, but I am saying that exercising our capacity to think in such a way every now and then is extremely useful. That is the goal of this series, getting people to exercise their capacity for deliberate, disciplined thinking. There are times for spontaneous association, there are times for explosive, intuitive action, but there are also times for deliberate, mechanistic, disciplined, rule-by-rule processes. So the problem that we are facing with is that we want to define inference, which is this weird, somewhat nebulous mode of thinking, and we want to capture it with an abstract system and turn it into an intentional, disciplined, mechanistic, computational method of processing information. Another reason why I prefer the information theory explanation over the classical one is because we can trick computers into processing information, but computers do not and cannot know what is true or false in any meaningful way. So we can forego, in this definition, the name truth. We can change it to have the designated value. All of those interpretations we can change true to value functions must also make the conclusion have the designated value. So we have taken a definition, the definition provided by these books, and made it more abstract and more general. And in doing so, we no longer have to worry about what truth or falsehood means in any philosophically distracting way. Because really, what matters is the relationship between the designated value structures. But we can go even further beyond. We can create a definition of inference that does not have to do with values or interpretations at all. We can define inference as producing a certain formula out of a set of formula by the careful and completely what's the precise what's the term I'm using for? Effective method described by a series of rules. We can have a definition of logical consequence that is based entirely upon the manipulation of rules. And that is the propositional calculus. Let me read out loud. Truth tables enable us to answer many of the significant questions concerning the truth functional connectives, such as whether a given statement form is a tautology, is contradictory, or neither, and whether it logically implies or is logically equivalent to some other given statement form. Now, we saw that this has a problem. Truth tables, while very visually striking and very clear, are computationally prohibitive. We could do them. They are valid. But it becomes very difficult to actually crank them out because truth tables grow exponentially. When something can be done, when something in mathematics can be done in principle, but the method is too prohibitive or takes too much time or too much resources, we call this untractable. I'm gonna write it in chat. So when something is tractable, that means there is a method to get to the answer. When something is untractable, that means, yes, there is theoretically a way of producing the answer, but it is too computationally exhausting, it requires too much resources or too much time to actually get there. Let me provide an example to maybe bridge the intuition. Tic-tac-toe is tractable. It is very easy to just sit down and brute force a solution to tic-tac-toe. Chess is not tractable. We know that chess has a solution. There is, theoretically, a perfect way to play chess, such that once this solution is found, chess will no longer have any value or entertainment. It will be a solved game. But so far, no method of figuring out the perfect game of chess has been established. Chess is an untractable problem. So truth tables quickly become untractable. If you have 16 propositional letters, that is 2 to the 16th, that is 65,536. Oh, yeah, new avatar. Sorry for the thing. That is my wrestling persona for lefties in fighting. Ah. Wait, no. There we go. I'm back. And it is something like that. Thanks for the stand-up and stretch. Yeah, lefties in fighting. It's a side show at Leaping Larry's. Okay, so where was I? Yeah, truth tables quickly become untractable. So, the more complex parts of logic we shall treat later cannot be handled by truth tables or by any other similar effective procedure. Consequently, another approach by means of formal axiomatic theories will have to be tried. So the book just introduces us this term, formal axiomatic theory. What does that mean? Formal means that the theory will not appeal to standard language or standard meanings of words. It will be defined on technical terms, and axiomatic is the funniest term in there, the most notable one. Something being axiomatic is a type of invention, a mental invention that was pioneered in the earliest forms of geometry, but really took off in the 19th century. An axiom means something taken to be true, but that is very abstract and not very useful to think about. What happened is that mathematics started being less concerned with trying to model reality and just exploring what could be done. If you define things in a certain way, if you change certain postulates of Euclidean geometry, you get different definitions of a type of space. And once again, I'm using space in a very abstract way, like I used in the first part of this session. So when we say that axioms are just things taken to be true, again, we're not talking about true in any rich or plentiful way. We're just saying, okay, let's just play with this set of rules and see what happens. Again, let's take as illustrative example chess. We can treat chess as an axiomatic system that defines how each piece is moved, how the game is won, and how pieces start. It would be absurd to call chess true. I mean, there's a thing we can call true chess or standard chess, but if, for example, you play with a different starting set of pieces, as some people do, that is still chess, it's just chess under a different set of axioms. If you play timed chess, that is classic chess with an extra axiom, which means that all moves must be taken under X amount of time. You can play fog of war chess, in which you can only see the space around your pieces. All of those things are different or added axioms in a way. or in the way of axioms that has taken to be used by mathematicians since the 20th century. So we can think of axioms as just structural inputs, statements that define the structure of the workplace you are going to be operating under. Things that define the rules of how to act and how things behave, not true in an metaphysically committed way. Although, as we have seen, the propositional calculus surrenders completely to the truth table method, yes, the truth table method alone is sufficient, but it is not practical. It will be instructive to illustrate the axiomatic method in the simple branch of logic. Yes, there are multiple reasons why we want to practice the axiomatic method in this baby logic. It's just going to prepare us for when we actually deal with a rich, complex logic and eventually set theory. So let's just take this as granted. A formal theory, is it a T or an F? I prefer, I don't know, well, it doesn't matter. The whole thing is a meta variable. Any formal theory, whatever, is defined when the following conditions are satisfied. A countable set of symbols, not symptoms, is given as the symbols of the system. Countable, in mathematical lingo, means infinite, and it is the smallest infinite. Countable means the size and order of the natural numbers. Basically, numbers you can count one by one by one by one by one in discrete hops, as opposed to the reals, which are dense. So we have an infinite amount of symbols, but it has to be the size of the first infinite. It has to be countable like the natural numbers. A finite sequence of symbols of the system is called an expression of the system. There is a subset of the set of expressions called the set of well-formed formulas, or waifus. Whiffs. You want to call them whiffs or waifus. There is usually an effective procedure to determine whether a given expression is a well-formed formula. Yes. We went through this in our second session. We said that any propositional letter is a well-formed formula. Any propositional letter with a negation, any well-formed formula with a negation preceding it is a well-formed formula as well. And any two well-formed formulas with a conditional, disjunction, biconditional, or conjunction, disjunction, conditional, and biconditional in the middle surrounded by parentheses are a well-formed formula. And that's it. That is our effective method for building well-formed formulas. There is a set of well-formed formulas called the axioms, the set of axioms of the system. Most often, one can effectively decide whether a given well-formed formula is an axiom. In such a case, the system is called an axiomatic theorem. What does that mean? Okay, so effective method is an open problem in mathematics. So far, our best answer is that effective method equals computable. And computable means that it can be expressed by either a Turing machine or by recursive lambda calculus, or there's a third equivalence which I forgot, but those are the main two. Okay, have a good time, Rupert. We're almost done, don't worry. And yeah, all the VODs are gonna be uploaded to YouTube, so watch there. So yeah, when mathematicians speak of effective methods, they are using that in a very specific technical term. So far, it means computable. But maybe in the future, someone will think of something that is an effective method, but somehow not computable. So far, this hasn't happened. So far we can treat effective method as synonym of computable. And computable intuitively means that it's an operation that can be executed following a precise set of rules through an algorithm without appealing to interpretation, semantics, or any sort of human ingenuity. If we have effective methods to decide whether something is an axiom or not, then the theory is called axiomatic. There are systems in which we cannot find such a method. And that is one of the most mind-blowing and interesting theorems proved in the 20th century. There is a finite set that goes from R1 to R to the n, so an arbitrary yet finite number of R's, of relations among well-formed formulas called rules of inference. For each rule of inference, there is a unique positive integer, j, an arbitrary variable, such that for every set of j well-formed formulas and for each well-formed formula beta, one can effectively decide whether the given j well-formed formula are in relation to beta, and if so, beta is said to follow from or to be a direct consequence of the given well-formed formulas by virtue of R. That is the reason why we went through this side road about logical consequence and so on. This is very abstract and very difficult to understand if you don't already know what this person is talking about. Thankfully, there's an example. An example of a rule of inference will be the rule modus ponens. Any formula follows from another formula and the implication of the first to the second. According to our precise definition, this rule is the relation consisting of all ordered triples. Okay, what does it mean? It means that the rules... Okay, first let me explain what modus ponens means. Modus ponens means that if you have a P, if you have an implication and you have a Q, and you also have P, then from this, using the modus ponens rule, you can... What word did it use? You can get as a direct consequence the letter Q. If it rains, I will get wet. It is raining. Therefore, I will get wet. It is the most simple notion of direct consequence that we have. If the first, the second, and I have the first part, therefore I must have the second part. Modus ponens is the name scholastic monks during the later half of the Middle Ages called this type of inference. The full name is modus ponendo ponens, which is Latin for mode of affirming by affirmation. I can affirm the consequent by affirming the antecedent. Because we know that this means that whenever this is true, then this is true. Oh, well, look at that. P is true. So, Q must be true. Now, the whole reason why we're defining consequence in terms of triplets and sets and direct consequence and all that jargon is because we don't want to appeal to true or false or any of those designated values. Because designated values are arbitrary and we may not always come to rely upon them, so we need a more general method for modeling inference. Whatever. It'll get to it later. So back to the mess of a definition. So these relations between well-formed formulas we call rules of inference. And a rule is not a rule for a specific case. It is a rule for every structure that matches with the rule. For example, earlier I made the most potent thing with P's and Q's, but it can be done with any well-formed formula. For example, not P implies not Q. Oops. Not P, therefore not Q. Again, what is here doesn't really matter. All that matters is the general structure of there being a well-formed formula and a well-formed formula. Here we call this well-formed formula 1 and we call this well-formed formula 2. And this relationship between well-formed formulas we call a rule. And the idea is that we can chain these well-formed formulas between premises and conclusion, and we can have an effective decidable method to see if the formula follows or doesn't follow from beta. Beta here is an arbitrary set of premises. If we can provide a set of rules that transforms a set of well-formed formulas into another, if every transformation is done through one of those rules, then we have that the end result is a direct consequence of the given well-formed formulas by virtue of those rules. This definition of logical consequence does not appeal to truth. It just appeals to properly applying a set of rules through an effective, by that we are taking to understand, computable method. So, in this understanding of logical consequence, something is a logical consequence of another if I can write a program, if I can write an algorithm to transform the premises into the conclusion by virtue of some well-defined rules. And that's it. And the immediate question that popped into my mind when I studied this is, okay, but how do we know that the rules preserve truth in the same way that we were preserving truth through the other definition? Well, turns out that is quite more difficult than it first appears. You will need to prove that every rule in your axiomatic system preserves truth under the first definition. And you will need to prove that this preservation applies to the countable, infinite cases or sequences of well-formed formulas to which it applies. So our rules are a general schema that applies to an infinite amount of sequences. So how do you prove something is valid for an infinite amount of cases? Well, for that, you need some very heavy-duty mathematical machinery. And here comes the funny part. You can only get to understand that machinery called mathematical induction once you have learned how to apply rules in this manner. So, what we have to do now is learn these rules so that we know what a formal proof, how a formal proof works. And this is extremely useful stuff. If there's one thing I want people to get from this series, is a more intuitive understanding of what a mathematical proof is and the many ways in which they can be done. We are now going to define formal proofs. Proofs that can be done in such a way that computers can do them. Proofs that do not require any ingenuity or creativity or interpretation. So, I will continue reading. A proof in our logical system is a sequence, an ordered sequence where there's a beginning and an end, of well-formed formulas such that for each instance, for each formula on the way on the sequence, either the formula is an axiom of the system or the formula is a direct consequence of some of the preceding well-formed formulas in the sequence by virtue of one of the rules of inference of the system. Basically, this means that the kinds of transformation I can have in a proof is closed. The only way I can get content, informational content in a proof, in a deductive proof, is whether something is an axiom, a premise, or a direct consequence of applying a rule to one of the previous. And that is it. A proof, under the information theoretic perspective, is a closed information environment. No new information gets in. All the information is therefore a breakdown or an analysis through rules of the information already present in the axioms or the premises. So, under the information theoretic perspective, a logical consequence is always a matter of access to the information that was already there. Something is a logical consequence of another formula if the total amount of information does not increase. Again, that is my personal understanding, that's my personal posture. It makes a lot of sense to me. It helps me with not engaging in a type of metaphysics I don't want to. And it matches perfectly the definition of proof that we just saw. Anyways, let us move on. A theorem of the system is a well-formed formula of the system such that the formula is the last well-formed formula of some proof in the system. Such a proof is called a proof of beta in the system. So, we get theorems by analyzing the axiom of the system through our set of rules. Any formula that we get by just merely analyzing or applying rules to our axioms is therefore a theorem. And this applies to mathematics, not just formal logic. That's why we can have theorems in piano arithmetic, we can have theorems in linear calculus, and so on and so on. Even if the system is axiomatic, that is, if there is an effective procedure for checking any given well-formed formula to see whether it is an axiom, the notion of theorem is not necessarily effective, since in general, there is no effective procedure for determining whether any well-formed formula beta, whether there is a proof of beta in the system. A theory for which there is such an effective procedure is said to be decidable. Otherwise, the theory is said to be undecidable. Again, technical terms. If we can prove that the system can prove things, and I know it's a very strange way to say, because we will be watching the system from the outside. If we can analyze and study the system and see that there are effective procedures for getting any theorems within the system, then that system is decidable. If we know something is a theorem in a system, but there are no effective methods to actually get there, then the theory is said to be undecidable. Decidable is not the same as true. Decidable is not the same as correct. Decidable means decidable. Decidable is a specific technical term, and that means that there is an effective procedure to get that theorem within a set of rules. The risk of this, or the interesting part, is that we can therefore conceive of things that are or should be theorems in mathematics, but we cannot get there by raw computational brute force. They are not decidable. And spoilers, most complex, or rather, any axiomatic system beyond a certain threshold of complexity is undecidable, or has undecidable theorems. Thankfully, in propositional logic, the system we're studying, that is not going to be a risk. Propositional logic is decidable, which also means that propositional logic is very simple. From an intuitive standpoint, intuitive according to mathematicians, so who knows, a decidable theory is one for which a machine can be devised to test well-formed formulas for theoremhood. Theoremhood means what makes a theorem what it is, whereas for an undecidable theory, ingenuity is required to determine whether well-formed formulas are theorems. Again, this is not a formal statement. That is a philosophical statement. Now, I think that is enough for today. We will start studying this is properly called metalogical language of a system. Let me tease a bit to what we're gonna study. We are not doing the schemas, that is torture. Okay, this is how real obsessive mathematicians can build an axiom schema, but we're not gonna do that. We're gonna learn through something called natural deduction. Oh god, okay, we're gonna have to use another book, because this one does not use natural deduction. This one uses the super painful 3-axiom schema method, which is really good for metalogic, but we're not doing metalogic, we're just doing plain old logic today. So yeah, next week we're gonna start with a more friendly notion of proof with a more friendly set of rules. Anyways, this was Samuel, your friendly internet uncle, that wants to help you get into philosophy, helping you get into mathematical logic. I hope you all enjoyed this session. I wish everyone an excellent weekend. Have fun. I think for homework I will share some night and names puzzles. Night and names puzzle for homework. I'll share them in my Blue Sky. Thanks, Anarkodako. Hope you have a good time. Bye-bye.